finally, let us summarize what we have learned in lecture 7. Right? So we have worked with a linear second-order ordinary differential equation with constant coefficients that is used to model oscillating motions. Right? So the main example that we had in mind is a weight attached to a spring, so a spring weight system or a spring mass system. So then the spring constant can be found by balancing all the forces, and here is the final answer. So then the right-hand side of the system of the differential equation is the external force or the driving force. So if there is no driving force, then we have free vibrations or free oscillations. If there is a driving force, then it is driven oscillations or driven vibrations. So then gamma here is the damping constant. So it appears due to friction in the system. Well, if there is no friction, then we are going to have undamped oscillations, which is hardly possible in practice. Then if the damping is too much, is too large, so then the friction is so heavy that there is no oscillation at all. This is called critical damping or over damping. Then if the damping constant is not too large, then there is going to be an actual oscillating motion, and oscillating as t goes to infinity, oscillations are going to decrease in amplitude. Right? And then there's still going to be oscillations, which means the graph of the function u of t is going to go up and down, and then we're going to have quasi-frequency. What is called quasi-frequency. So this is the coefficient in the sine and cosine. So this means that the solution of the system is going to have e to the power some minus lambda t times cosine of mu t. So this mu is found from this formula. So the bigger it is, the more frequent the oscillation is. Well, and finally, well, the driving force is usually a periodic function. So then a resonance is the situation when the frequency of the driving force is the same as the frequency or the quasi-frequency of the free system.